Straightline approximations and just a summary of what it is. So straightline approximation is always used in getting what we refer to as in constructing board plots. We use them in constructing board plots, and then this one as opposed to the calculations that are always done in board plots. In this case, we simply use straight lines with the gradient depending on the term of that particular transfer function that you are given. So when you talk about the straight line approximation, I want us to consider this equation. So you can talk of, let's consider this, Ej omega is equals to K into 1 plus J omega T1 into 1 plus J omega T2 all over. You can talk of J omega plus or minus N into 1 plus J omega TA. So those are always the terms that are always involved as far as the transfer function is concerned. So if you look at that equation, then the numerator and the denominator have got three basic factors. One of the basic factors that we can talk about is the constant gain. So the three basic factors that we can talk about here, we have the constant gain K, the constant gain factor K. So the first one is the constant gain factor K. Then the other one, we can talk about what we refer to as the poles or the zeros from the origin. You can talk of poles like that, poles, stroke zeros, poles or zeros from the origin, and this one is represented by J omega plus or minus N. So that is what we can talk about in that case. And then we also have a simple zero or simple pole. So the other one can be simple zero or simple pole. So those are the three things that we are going to look at. So we are going to look at how do we deal with each and every factor. So we start by looking at when we have a constant term A. So we can talk of constant gain factor K. Constant gain factor K. So when you look at the constant gain factor K, so the constant gain factor K is normally frequency invariant, which means the frequency does not change, and the magnitude will always be given. So if you have to do that, to draw a straight line for that, so you are supposed to get the magnitude n, or you can talk of its value in terms of Lm. So when you talk about the constant factor K, then this one is always given. We've said that it is frequency invariant, and the magnitude of this is always given by the magnitude is equals to 20 log to base 10 of K, which means, for example, if the constant K was 1,000, then we are going to say 20 log to base 10 of 1,000, and then you get the value. And then that from that is now where, if you have your board plot in that manner, so this is now what you are going to get. If you have your board plot in that manner, so that is your 0, this is 180. So to draw a straight line for that, it will be a parallel line to the 0, 180 degrees line with the value of 20 log to base 10 of K. So in that case, if it is 1,000, then 20 log to base 10 of 1,000, I think it will be 60. Is it? So you will come here from your scale where 60 dB is. That is where you are going to draw that line, and that is what is meant by 20 log to base 10 of K. So that is how you will be dealing with all the values as far as it is a constant. Of course, if it is a negative term, if it is a fraction, like let's say 20 log to base 10 of maybe 0.5, then of course it will be a straight line downwards on the negative sides of the log magnitude scale. Sawa sawa? So that is how you are supposed to deal with that particular first term. And again, for the angle, it does not have the real value, and therefore it does not have the imaginary value. So tan inverse, we have k, comma 0. Tan inverse of, it's going to be, the real term is k, isn't it? Yeah? Then the imaginary term, tan inverse is always tan of 0, isn't it? And therefore the angle will be 0. So in that case, angle will be 0 degrees. So any time you have that, then you should be able to get the value of the constant term, and then the angle will be 0. So that is how you are supposed to deal with the constant gain factor k. So let's look at how are we going to deal with poles and zeros from the origin. Poles and zeros from the origin. Poles and zeros from the origin. So we can talk of poles and zeros from origin. So if we talk of poles and zeros from the origin, then we are simply talking about, we can start with the pole. So you can say, let the pole be 1 over j omega. I believe you still remember what a pole is. Are we together? You still remember what a pole is? Any value of s that makes the whole of j omega to be infinity. Yeah? Is what a pole is. So which means the poles always appear at the denominator. Is it okay? Are we together? So the poles always appear at the denominator. So anything that will make this value to be infinity, anything that will make the whole of this term to be 0, or the whole of this term to be 0, will be referred to as a pole. So if you talk about 1 over j omega, then in that case, we can talk of the magnitude. So what will be the magnitude? Magnitude of this will be given by 20 log to base 10 of the magnitude of 1 over j omega. Magnitude, so we must represent it by that. The magnitude of 1 over j omega, which in this case, because of that negative, it will be minus 20 log to base 10 of omega in decibels. How would we get the magnitude? 0 will be 0 comma omega. 0 squared plus omega squared. And of course, because it is negative, then you get the square root. So it will still just be omega. But the magnitude, we don't usually show it in negative. So the only thing that will be negative will be the log. This one shows that the gradient now is negative, which means it has got a gradient of negative 20 dB per decade. A decade is between, let's say, 0.1 to 1, that is a decade. 0.5 to 5, that is a decade. Which means within 0.5, if maybe the corner frequency was 0.5, within 0.5 to 5, it should have a gradient of 20 dB. Tunaelewana? Itakuwa imeshuka 20 dB in that particular decade. Sawa sawa? Then from there, we can talk about, that is now the magnitude. And when you plot this, then plotting this, you are going to have a negative. It will be plotted. It is a negative straight line with a slope. So this one, as you plot it, it is a negative straight line with a gradient of negative 20 dB per decade. It's a negative straight line with a gradient of negative 20 dB per decade. So, in the other case, we say that it was a straight parallel line, right? It's a straight parallel line. Now, in this case, when we have a value in the denominator, and we are talking about now where maybe we talk of a transfer function, maybe we can look for a transfer function that we will be comparing with. So let's consider that maybe we talk of a transfer function like, let's say 1, let's talk of something like, we can talk of a value of 10 all over s into 1 plus 2s into 1 plus 0.02s. So if we talk about that, then this one is the constant k that we were talking about. So if you have to draw this, it will be 20 log to base 10 of 10, which is just 10, just like we said in your board plot. You'll have that and come to where 10 dB is and draw a parallel line. So what we are discussing is here. Are we together? So if we have this, then in that case we are talking about 1 over j omega, because you can see that it is down there. So in that case we are going to draw it by considering this. It will be a negative line with a gradient of negative 20 dB per decade. And therefore we are going to have a slope of negative 20 dB per decade, which under this particular slope that we are talking about, it is always 0. It's supposed to read 0 at 1 rad per second. It is supposed to read 0 at 1 rad per second. At omega is equals to 1 rad per second. So that is how you are supposed to deal with that particular term. So when you deal with the poles, then it has got a negative gradient of 20 dB per decade. What if we have zeros? So you can let that one to be a 0. So if you let, yes?
Does it mean now, before the transfer function that we've been dealing with, like this one,
Yes.
approximation, this line must be there, the point log.
I'm not saying it is. It will depend on the transfer function that you are given.
Most likely when the s is there. In the denominator.
Yeah, as long as s is there. This one can be rewritten as 10 all over j omega into 1 plus 2 j omega into 1 plus 0.02 j omega. We know that we usually replace s with the j omega. So if you rewrite it in terms of j omega, then that is now what it becomes.
Finding the magnitude.
Yes.
The value of omega.
Yeah?
Will you get the value of omega? It will be just omega.
You will not get the value of omega. You will use the straight line in order to get your graph for the gain curve. The straight line is always used to get the gain curve. Right? So, as long as you have the j omega that, then you will draw the straight line as described. Right? As a negative straight line with a gradient of negative 20 dB per decade and 0 dB at omega is equals to 1 rad per second. Are we together? So that is what we are supposed to do. Then we can talk about the other one. And what is the angle here? From what we have been talking about, what is the angle? Can you tell us what the angle is? Yeah? The angle is 0, omega. What is the angle? Tan inverse of omega. Omega can be any value. What is the tan inverse? You can take a good example, 0, 1. What is the value of the angle? Yeah? So the angle will always be 90. So you can say the angle equals to 90 degrees. The angle is a constant angle and it is equals to 90 degrees. So phi in this case is constant and it's equals to 90 degrees. And of course we can talk about it as negative 90 degrees. So we can talk of it as negative 90 degrees because we say that all these angles are angles of lag. Then we can go ahead and look at, in the first case, we were dealing with a pole, right? Assume now you let it be a 0. So you can let j omega become a 0. So if you let that one to be a 0, then should you let it to be a 0, then what you are going to say is that now what was actually happening here now becomes the opposite. You will have just a curve like this one, but now instead of that curve being negative, it is positive. So, and like now, if we have the curve for the first case, when we consider it to be a pole, what we are saying is that it is supposed to be 20 dB per decade. So which means if you start it from 20 here, let's say that is 20 dB, then you come at 1 rad, it should be 0. So you have your straight line in that case. Right? So that is how you develop the straight line. In the other case, in this case, of course, now the only thing that we'll have, it will be a positive straight line. Huh? Are we together? In the case where we consider this one as a 0, if it is at the top. So in this case, we have something like kj omega there, right? Or maybe we have ks, or we have 10s, right? Are we together? So there is s there, there is that there. So if we have s up here, then now we are considering it to be a 0. And if we consider it to be a 0, we'll have a positive straight line. So in this case, we are going to have a positive slope. A positive slope of 20 dB per decade, and the angle is constant, which is 90 degrees. Is it okay? So if you draw it now, then you are going to have here, it starts from negative 20 here, yeah, positive gradient, that in that manner. So that is now what you are going to get. So that is what you are going to get in that case. So that is if you consider the poles and zeros from the origin. What of if we consider the simple poles and simple zeros? Simple poles and simple zeros is where we have both the two terms. We have both the real and the imaginary. Are we together? So in this case, we usually have two straight lines. In this case, we usually have two straight lines. One of them, it will be 0 until it reaches what we refer to as the corner frequency. You remember how to get the corner frequency? Like in this case, we are talking of a term of like either that or that. The corner frequency is obtained by getting the reciprocal of the term with the j omega. Like in this case, we are going to get 1 all over 0.02, which is 50. So if that is the case, then unlike this one, if you have to draw that, unlike this, if you have to draw that, then what you are going to have is, assume this is now what you have as your board plot. Assume this is now what you have as your board plot. So it will be 0. It will be 0 until it reaches the corner frequency. Like in that case, it is 50. Are we together? So let's say that at that point we have 50 rads. Yeah? Then after that, depending on whether it is a 0 or a pole. Yeah? Is it a 0 or a pole? Any term that is at the denominator is a pole. Any term that is at the numerator is a 0. Remember we said any value of s that will make the overall transfer function to be a 0 is a 0 of that function of s. It is a 0 of the f of s. And any value of s that will make the whole of that transfer function to be infinity is a pole. So if we say that all the poles have got negative gradient. Are we together? So that is the first thing that I need us to understand. All poles have negative gradients and all zeros have positive gradients. With the value of the gradient determined by the term itself. If it is a simple, all simple poles and simple zeros will always have gradient of 20 dB per decade. Sawa sawa. Then all, if now, let's say this one is now raised to power 2, then the gradient will now be that 20 dB per decade will be multiplied by 2 so that we get 40 dB per decade. If it is cubed, it will be 60 dB per decade. And remember what the decade is. The decade is a multiplier of 10. From 0.1 to 1 is a decade. From 0.6 to 6 is a decade. From 0.9 to 9 is a decade. So that is which means if maybe the corner frequency, like in this case, is 50 rads per second. Are we together? What is 50 rads multiplied by 10? 500. Is it? It means that between 50 rads and 500 rads, there should be a slope of covering 20 dB. Diagonal slope covering 20 dB. Are we together? Yeah? So that is what we mean by 20 dB per decade. So we were saying that considering that one now as a 0, then we are going to have a gradient, positive gradient of 20 dB. So we start from here. Positive usually go up. Start from there. And it goes that way. Yeah? Again, the same thing will happen. It will be 0. At 0 dB. 0 dB is here. Yeah? On 180 line. At 0 dB, it is going to be 50. At 0 dB, not really 50. This one is going to be, so we've said we were drawing for the other one. So this one is going to be that. That is when we have both the terms. 0. So we were talking about this. 0. It is 0 at lower frequency until it reaches the corner frequency of the reciprocal of that. When it reaches that, because it is a pole, it should take which direction? Down. Down. It should come down. Because it is a pole, it should come down. Which means for it to get to 20, it should get to 20. If you were to use the scale, where it gets to 20 should be 500 rads.
And when it reaches at 500?
Yeah? At 500 rads, 50 times 10 is 500. So between 50 and 500, it should cover 20 dB diagonally, downwards, because it was a pole. Are we together? If it was a 0, then it will be 0, yeah, until it gets to 50 rads. Getting to 50 rads, for it to cover 20, then at 500 again, it will be that. Is that okay? So generally, those are the kind of straight lines that we are going to draw, so that you get the. So how the angles that you are going to get will be that tan inverse of. So it is like in this case, it will just be tan inverse of 0.02 omega. And then when you will be getting the values of omega that you can always find by yourself, then you will be filling the angles in order to come up with the phase curve. You will be filling the angles in order to come up with the phase curve. I believe that you already have the notes, so you can go through. I think you can see that you have them, so you can go through and then get what we can do. So I want us just to get straight to an example and see how it can be done. So let's get straight to an example and see what can be done. So consider that. So the first thing that maybe we can do is to change S, all the S's into j omega, and if we do that, we are going to have j omega is equals to 10 all over j omega into 1 plus j omega into 1 plus 0.02 j omega. So that is what we are going to do. So we are going to look at each and every specific term. So from your board plot, so assuming this is your board plot, so this is your board plot, so you need to put the scale 0, 180. For most of the straight line approximation, I usually prefer that at this corner you start with 0.1 because of the 1 rad per second that we talk about. Right? So 0.1 at the corner so that 1 rad per second can be in between, because 1 rad per second is always very, very key, especially when you are doing straight line approximation for the terms that are at the origin. So you can get 0.1 there. Then we can look for the first term. So you can make the scale for the board plot. Draw this line, get the angles here, get the magnitudes here. Then from there we can get to what it is here. You can, from the equation, you can go to up to around, for this I think it will be around 40. The maximum will be around 40.
Yeah.
Me, I can see it, but maybe you may not be able to see it. So you can have a maximum of, let's say, 50 for this side. 50 dB. Yes? No, that one is for the rads. I'm talking of this. This is the log magnitude. This one you can start with 0.1. I know the graphs that I gave you. That is a scale for log magnitude. That one you can make. The whole of this is log magnitude. Not necessarily. You can divide it into two so that both of them can be 50-50. And also make the scale for the angles. Not even finish writing the equation. Huh? So maybe before that we can finish writing the equation. Use asymptotes to draw board plot. 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 Full stop. From the plot, determine. From the plot, determine. From the plot, determine. 1, gain crossover frequency. From the plot, determine 1, gain crossover frequency. From the plot, determine 1, gain crossover frequency. 2, phase crossover frequency. 2, phase crossover frequency. 3, gain margin. 3, gain margin. And finally 4, phase margin. 4, phase margin. Fourth one should be phase margin. So in this case, we have the constant term, which is the K, which is 10. So for us to draw that, so for the constant term, and say for the constant term, we need to get the value of k. The log magnitude will be given by 20 log to base 10 of 10, which is, for the constant term, we are going to get that 20 log to base 10 of 10, which is simply 20 dB. In this case, it will be 20 dB. So in that case, you are going to come to your board plot. Then on your scale, there is where you have, on your scale where there is 20 dB, you draw a parallel line. So are we doing that? On your scale where you have 20 dB, you draw a parallel line. That one is for the constant term here. You're supposed to draw a parallel line. We say that that is always frequency invariant. It does not change with frequency, it is constant. So you're supposed to draw that. And of course, you should be making the scale appropriately. So after decade, the first one should be 0.1. The next one should be 1. The next one should be 10. So you can see that between 0, that, and 1 is a decade. That is a decade. 100 is a decade. And then there, maybe 1,000. Between 1,000 and that, maybe and 100 is also a decade. So in that case, that is how you deal with the constant term. So even if you are given any value, as long as it is a constant term, you are supposed to deal with it the same way, so that you get the log magnitude, 20 log to base 10 of that particular constant. So after getting the constant term, now we can go to the second term, which is the j omega, and we can see that the j omega is at the denominator, and that one signifies that it is a pole or a zero. Eh? Is it a pole or a zero? It is a pole. So what did we say about the straight lines for the poles?
Negative.
The straight lines for the poles are always, they have negative gradient. And if it is a simple pole, what is the gradient? It will be negative 20 dB per decade. Simple pole means that it has got a power of 1. A simple pole means that it has a power of 1. Are we together? Yes. A simple pole simply signifies that that particular term that we are talking about has a power of 1. So all those have got power of 1. Yeah. If it is squared, then now it is not a simple pole. And that is now where we said that the gradient is always plus or minus n. Yeah? You remember? J omega plus or minus n. That is the term that we use. So the gradient will be plus or minus n, 20 dB per decade. If n is 2, then it will be plus or minus 40 dB per decade. If it is 3, plus or minus 60 dB per decade. So now we can go to the other one, the term j omega. The term j omega, we say that it is a pole, and it is a simple pole at the origin. So it is a simple pole at the origin. A simple pole at the origin, we said that it has got a negative gradient of 20 dB per decade, and again, it reads 0 dB at 1 rad per second. So that one will give us 2 points. It reads 0 dB, so 0 dB at 1 rad per second. Is that okay? And it has got a negative gradient of 20 dB per decade, which means after a decade, that is between 0.1 and 1, it should go down up to 20 dB. So that is what we have, and then you extend the line. Many a times when people are asked this, there was a time I gave a question whereby it was 60. The straight line was 60. And then everyone was drawing for me. From 60, the next one, everyone was drawing that. That is not 20 dB per decade. Eh? That is now 60 dB per decade. So don't do that. Eh? Ensure that you maintain 20 dB per decade. Even if this one was 1,000. Yeah? I will draw the straight line as 60, then 20 dB per decade. You start from here. Are we together? Yeah? What I'm saying is that what we have drawn here, it is just a coincidence that the value of K was 10. Are we together? And this one also has got a gradient of negative 20 dB. That is the coincidence. If I change this value, maybe it will be 1,000. Then for that, I will have 60 for the straight line. But I will still maintain 20 dB per decade for the other one. Huh? It does not mean that they must intersect that way. If this one it was 1,000 instead of 10. Yeah. You have to get 20 log to base 10 of K. Whatever value of K that you are given.
That line has a gradient of 20.
Yeah, for the 60 it will just be that way. Yeah, the other one will be remain the way it is. Huh? So you don't, what I'm saying is that what we have here does not mean that they must always meet at that point. Huh? Are we together? It should be drawn as per the terms of the transfer function that you are given. Clear? Clear? So, after drawing that, we go to the next one. We go to the next one. We go to the next one. The next term. So which one is the next term? 1 plus j omega. So in this term, it has got both the real and the imaginary sides. If it has got both the real and the imaginary sides, then there is one thing. We say that in that case, you have how many straight lines? 2. It will be 0 until it gets to the corner frequency. And the corner frequency is determined by the reciprocal of the term for the j omega. What is the term for the j omega? 1. So 1 over 1 is 1. Are we together? So, in that case, what we are simply saying is that it is going to be 0. Are we together? Until it gets to 1 rad per second. It is going to be 0 until it gets to 1 rad per second. Huh? After getting to 1 rad per second, because it is a pole, all poles have negative gradient. It will follow the same line here, which means, in actual sense, on this line, you are going to have 2 lines. Are we together? 0 until it gets to 1 rad per second. After getting to 1 rad per second, it is going to have a negative gradient of 20 dB per decade, which means it is simply going to be on that particular line. Huh? So in that case, from here, when you will be adding this line, you will be adding it twice because there are 2 lines. There is one line that is superimposed on the other one. Huh? Is it clear? Are we together?
They are just using that magnitude.
Yes, because they are simple. We say that all simple terms use the magnitude of 20 dB per decade. If they are raised to a certain power, then it will be that power times 20 dB per decade, depending on whether it is a pole or a 0.
Take it now.
Yes?
Take it now to be 40 dB per decade. Draw that line. Let us
40 dB per decade?
Yeah.
You are asking how to draw 40 dB per decade? So it simply means that if that is 40, 0.1, it means that at...
It is start at 40 now. It will be start.
Yes. What it means is that at that, if it was for j omega. What we are saying in case of that, yeah, it will start from 40, hit 0 dB at 1 rad per second, then so it will be steeper, right? Yes, so it will be steeper. So that is why we say that the gradient is determined by plus or minus n dB, where this n actually stands for the power of the term. So what of the other one? What is for the second one? What is the corner frequency?
60.
Yeah?
50.
50. So it will be 0 until it gets to 50. Let's say 50 is here. Are we together? 0 until it gets to 50. So let's say that is 50 rads per second. Huh? When getting to 50 rads per second, it will have a gradient of 20 dB per decade, which means at 500 here. 50 times 10? 500. Huh? So at 500, it should read 20. So can come to that 20. Let's say that is 20. And at 500, then we join to get it straight line. Yeah? You get the corner frequency, which is 50. At lower frequency, it will be 0 dB, which means it is 0 until it gets to the corner frequency of. Yeah? Even that one was 0. The one that is black was 0 also. It has got two terms. This one has got both the real and imaginary term. So it is 0 until it gets to the corner frequency. This one does not have imaginary term. That is why it starts from here. The other one goes to 0 until it gets to this. Then from there, we have that. This one 0 until it gets to the corner frequency, which in this case is 50. Then from 50, negative 20 dB per decade, because it is a pole. Then from there, we have finished the terms. Huh? From there, we have finished the terms. So what we need to do is to draw our log magnitude graph. Yeah. Hmm?
Okay. From 50 to 500,
Hmm.
multiply by 10.
Then there should be 20. The slope should have covered 20 dB for it to have a gradient of negative 20 dB per decade. Zero up to that.
Okay, fine.
Yeah?
I don't know.
Then from there up to 500, it should be?
Oh, okay, it will cut at 20.
Yes. Yes.
Okay.
Have we drawn that line? What? What about it? Are you able to get where 50 rads is? Come to 0. And maybe if you look at several maybe references, you will not find that that line of 0 is there, is drawn. Huh? So you just simply find it starts from here, right? The other one starts from here. So that is what will always happen. But as long as you have a simple pole and a simple 0, simple pole and a simple 0 will always be 0 up to that particular point where you get the corner frequency. Where you get the corner frequency, then at that particular point, that is where the gradient will be there. If it is a 0, it will go up. If this one was a 0, it will go up. Huh? But if it is a pole, it will come down. And because it is a simple pole, all simple poles and simple zeros have got a gradient of 20 dB per decade. It is the direction that is different. For the pole, it is negative gradient. For the zero, it is positive gradient.
My question is, what determines that hii curve itakulia ukunde huku chini sasa ama inaenda yenyewe?
That is what I'm saying. For poles, gradient. For the poles, the gradient is, it comes down. For the zeros, it comes up.
Ishike wapi chini?
That is what we are saying. Per decade. A decade means between maybe 50 and 500. Between 1 and 10. Between 0.1 and... So if your first point is here, and you need a gradient, your first point is at 50 rads per second, and you need a gradient of 20 dB per decade coming downwards. What is 50 times 10? It means that at 500, it should be 20 dB for you to have that gradient of 20 dB per decade. Because between 50 and 500 is a decade. And at 50, it is 0. So what will be the reading at 500? 20. So you simply have that and then join the points with a straight line. Through with the straight lines, we can now tabulate and come up with the gain curve. We can tabulate and come up with the gain curve. So to come up with the gain curve, you can choose some of these particular frequencies. It's like we can talk of at omega is equals to 0.1 rad per second. So what will be the total gain? So in this case, you are going to add the values of all the straight lines that are in that particular frequency. So I'll come to the frequency of 0.1. Are we together? I'll get my readings. Which straight lines are there? There is the one reading 20 and there is another one reading 20. Are we together? Yeah? The one coming down, reading 20. This one, reading 20. Yes? Yeah?
You started drawing a line for the corner frequency
Yes.
before the curve.
Yeah.
So my question is, before you draw the curve, the angles there, are you supposed to consider?
No, we are going to come to the angles. Yeah.
So you can just choose anywhere in that curve.
These ones will lead you. We are not talking about it. These ones will lead you. Then after that, in some cases, you are always told the frequencies to pick. But if you are not told, you are at liberty to pick any. And get the values for the angles, as well as the values for that.
Our case here,
Yeah.
we have 1 and 50.
Yeah. No, you are still allowed to choose even 1, 10. Yeah? And get the corresponding angles for that. We'll come to the angles and we'll see. But for the like now we are talking of the frequency, we want to get the gain. So what we were saying, for this, we take 0.1. Are we together? 0.1. We look at the straight lines that are 0.1. If you look at it, this one coming down here, it is reading 20. Is that true? At 0.1. This one that is constant is also reading 20. So at that, what is the gain? So at 0.1, Lm is going to be 20 plus 20, which is 40 dB. So you will come to this. Get to where 40 dB is. Put a mark there. Yes.
What about the two?
Which two?
The two lines.
These ones.
Yeah.
Are they here? Are they at 0.1? If we talk of 0.1, we look at it straight. If I talk of 1, I will look at it straight. If I talk of 10, I will look at it straight. Yeah? So if I talk of 10, I will be doing that. Then I'll add that. At this point is 0. At this point is, I get the reading from the scale that I had. And remember here we had 2 lines. Are we together? So we take it twice. Is it clear?
So our main concern is just on the corner frequencies and the dBs,
Yes.
but not the angles.
Angles we are going to draw, but later. Yeah? We first of all have to get the gain curve. As I said, we said that the straight line approximation is always used to get the gain curves, right? The angles, we are going to get the angles. You remember we were talking of, like in this case, we know that the angle here will be 90. Are we together? The angle here will be tan inverse of 1 omega, tan inverse of omega. The angle here will be tan inverse of 0.02 omega. So that is how we are going to get the angles later on, after choosing particular frequencies. Yes? Yes?
Umenieleza ni 20 but sijaipata. Na hii sasa. Itaenda hadi wapi? Nataka
With how we get 40? Yeah? Are we all satisfied with how we get 40? Because the next thing is that I'm going to let us choose a frequency, and then we do you get the value and marker. So let's see. Let's pick 1 rad per second. All of us, let's pick 1 rad per second, and then add all the values for 1 rad per second. What will it be? So, so for that, pick a straight line. So what will it be? 0 plus 20. So it will be 20. So come to 20 there, put a mark. And it is just that simple. We are together? Then pick another. Pick 10. Pick 10. Pick 10. Pick 10. Pick 10. I believe all of us are there. Pick 10. 10, right? So if you pick 10, that way, remember, at this point we had 2 lines. We had the line for j omega and also the line for 1 plus j omega. You remember that? So which means when you are taking this value, you take it twice, right? So if this reading at 10 here is, let's say, minus 15. I'm just giving an example because mine is not to the scale and I'm not able to get there. So it will be minus 15, then coming to that, there is no other, plus 20. Is that okay? So this is going to be minus 10. So at the frequency of that, I'm going to have a total value of minus 10. And then I come to that and put my minus 10. Is it okay? Hmm? Yeah? It is minus 20.
plus 20,
E. Yeah, this 20. So if you choose this, or this one plus 20. If you choose this, I don't know, from your scale you can get this value. That is at 10 rads per second. What is the reading here? Negative 20. So we have negative 20 twice. Huh? So we have negative 20 plus 20. Is that okay? Is that true? So if it is true, then it means that at 10 rads per second, we are going to have negative 20. Is it? So you mark that negative 20. Mark that negative 20. You should do that until it crosses this line, because this line is very important. It is where we determine our stability parameters. Yeah? So maybe we can go ahead. We are at 10. Huh? Can we try at 50 and see? At 50 and get the values. At omega is equals to 50 rads per second. At omega is equals to 50 rads per second. Negative 44. Yeah, it's okay. So plot it. Plot it. Then after you've gotten all those values, now you join straight line. Huh? Freehand. Huh? You join the points freehand. So join the points freehand. Then this one, what you are now having after joining freehand is the gain curve that you are drawing initially from having the frequency and the gains in dB. So that is how you get the gain curve now. So those points that we've marked earlier as we were picking the frequencies, that is what we now do. I told you this thing is very, very simple. Very simple. But at times, people just take it to be very difficult.
It will depend. The
Huh?
teacher who taught you diploma.
So I want us to look at how do we get the angle. So I'm going to give you a general formula for the angle. You simply insert the value of omega and you will be getting the angles at all the frequencies. Huh?
Omega is not your already.
Yeah, you can simply substitute. So this is how we are going to get the angles. So the angle phi, are we together? Will be given by, we are going to get it from the first term. From the first term, we have 10, yeah? It is only the imaginary, it is only the real value, which means the imaginary value is 0, and we usually get tan inverse of 0, which is simply 0. Are we together? Yeah? Are we together? Minus, it is minus because we are using the De Moivre's theorem. This one is up, that is down. The angle's down here, we subtract. Is that okay? Minus, what is the angle here? It will now be minus 90 degrees. Do we all agree with that? 0, we've obtained 0 from here. We obtained minus 90 from here. Is that, yeah? Inverse of yeah, inverse of 1. But that one is only if omega is 1. So it is 0, omega. Yeah? So it is tan inverse of, no. Which one is it? The imaginary 0. Is that true? Are we together? Then that one is?
0 is the real value.
0 is the real value. So the imaginary is omega. So it will be tan inverse of y over x. It is always tan inverse of y over x. Huh? Sindio? Which is now tan inverse of infinity, which is 90. Right? Then we come to this term. For that term, because it is down with the 90, it will also be minus. Huh? And then it is going to be tan inverse of, so like in this case, we have 1, comma, yeah? Omega. Yeah? Is that okay? 1, comma, omega, which means it's going to be tan inverse of omega. So in that case, if omega, like in this case, if omega was 0.1, you simply substitute with 0.1. Huh? Is that okay? Minus, because that is still also at the denominator, 1, comma, 0.02 omega, which is now going to be simply minus tan inverse of 0.02 omega. So this one is the expression that if you insert the values of omega, will give you all the angles. So we can again start with the ones that we have used in order to get the gains, huh? To get the values. Like for example, if I have it at omega is 0.1, then I will have at omega is equals to 0.1, what will be the angle? Phi will be 0 minus 90 degrees minus tan inverse of 0.1 minus tan inverse of 0.002. Is that okay? So I've simply taken this formula. This is now the general formula that we have obtained from the transfer function, and then now I've customized with the value of omega. Is that okay? So here the value of omega does not apply, but now you can see this one 0.1, yeah, then this one times 0.1, it becomes 3 decimal places. Huh? So that one you can do it for all the frequencies that you have used in order to come up with the gain curve. And then from there, plot those values and come up with the phase curve. Huh? Simple?
What about if it is squared?
If it is squared, it will be multiplied by 2. The angle will be by 2. Instead of minus 90, it will be minus 180. So for the frequencies, what did we get at? We got the frequency of at omega is equals to 1. What did we get? At omega equals to 1, what did we get to be the log magnitude? Yeah? Yeah. Phase. Not angle. Not angle. Gain. What did we get to be the gain? 20 dB. At omega is equals to 10. Negative 20 dB. What was at omega is equals to 50? Negative? Negative 68. So for that case, you are supposed to come up. So the first one was 40. So the other one was 20. So you'll come to negative 20, maybe down here. At omega is equals to 50. So negative 20 here. Then we join that freehand. So that is what you are supposed to join, freehand. And of course, it is good for you to name it that this is gain curve. Name it as gain curve. Then when you come to the angles, we say that at omega is equals to 0.1, we had an angle of 95. So 95, so maybe you can have maybe 95 there. Coming to that, at omega is equals to 0.1, maybe you have 95 there. Then you can come to, at omega is equals to 1. What was the angle? Negative 136. So at omega is equals to 1, where the angle is equals to negative 136. So you come to that, look for where 136 is. Maybe here, can talk of that. So there, and then you do all that for the angles, and later on you join them free hand. You join them free hand. What is your gain margin? For this case, I'm just going to go through it very, very fast. And then from there, you are going to have it so that you can draw it. So the equation here, I'm going to write the equation, and then we see what is there. So if you look at this, then you must be very lucky because you have been given the angles in degrees. So you will not need to calculate the angles in degrees again. So what you are supposed to come up with is simply the gain curve. And just like it is, you can see, you have to convert this maybe into j omega, so that you are going to have 10 into 1 plus 0.1 j omega all over j omega into 1 plus 0.5 j omega times 1 plus 0.2 j omega. So that is what you are supposed to do. So generally, if you have that, then simply what you are going to have is something like that. So that is your board plot. I said that specifically when you are using the asymptote curves, always start with 0.1. It makes the work easier there. Are we together? Yeah? So that if you look at 0.1, of course, this one it is easier to choose 0.1 because from the graph you've been given this value 0.5. So it is easier to use 0.1 so that 0.5 appears between the two ones, the first two ones on the left. Yeah? Then from there you have your line there, 0, 180. Then you look at that. Constant term, 20. For the constant, 20 log to base 10 of 10. So it is 20 dB. You come to where 20 dB is. Yeah? Parallel line. You are through with that. Is that okay? The second term here has got both the two terms. It has got the real and the imaginary, and the term that is on the j omega side is 0.1. Is that okay? So we have to obtain the corner frequency. So the corner frequency, we get the reciprocal of that, which is 1 over 0.1, which is 10. So it will be 0 until it gets to 10 rads per second. Right? 0 up to 10 rads per second. When it gets to 10 rads per second, is it a 0 or is it a pole? It is a 0. So what is the direction? Up. Positive gradient. Is it clear? Yeah? So if it is 10, where do we get the next point? It is simple. So it has got a gradient of 20 dB per decade. Is it okay? So 10 times 10 is, so at 100 it should be reading 20 dB up. Simple. So come to 100 here. Come to that. It should be reading 20 dB. Join. You are through with the second line. Huh? Come to the other line. This is what we had drawn before. Is it okay? Negative 20 dB per decade because it is a pole. Yeah? And it is at the origin. At the origin means that it does not have the real part. So it is starting from there. At 1 rad per second, it should be 0 dB. Sindio? At 1 rad per second, 0 dB. Join that in that manner. Is it okay? Come to the next one. Corner frequency 0.5. Huh? Yeah? 1 over 0.5? 2. 0 until you get to 2. Let's say 2 is here. 0 until you get to 2. Is that okay? After that, it is a pole. Negative 20 dB per decade. So, here is 2. Where should it read 20? At 20. See? Yeah? 2 times 20 will form a decade. 2 times 10 will form a decade. 2 times 10 will form a decade. Then, at 20. This is 2. 0, corner frequency is 1 over 0.5 at 2. Yeah? Times 10, 20. So, at 20 it should read 20 dB. So, unakuja hapo 20. Then, let's say at 20 there, it should read 20 dB. So, from there, draw the line. Right? Come to the last one. The last one here is 0.2, right? 1 over 0.2, 5. 0 up to 5 rads per second. Let's say 5 rads per second is here. 0 up to 5 rads per second. 5 times 10 at 50 should read 20. You get your next point. Just come to at 50 there. It should read 20. So come to your next point. So it should read 20. Let's say 20 is here. Then draw that. Huh? Yeah? Add. Come to that. Add. So there we have 20, 20, 40. Here you may have another value there. So you just pick points. Huh? But I would advise you pick these points. Right? Are we together? At omega is equals to 0.5, plot it. At omega is equals to 1, let's say here, plot it. At omega is equals to 2, plot it. Then from there, join to get the gain curve. Then use this graph. Yeah? Use this table to get the phase curve. Determine the stability using in a conventional way. And you should be through with everything. Simple? Yeah. Can we try it? I want to leave you trying it.